Hi, welcome back. In this video, we are going to be doing some examples of sampling distributions, comparing the difference between the sampling distribution for sample proportions and the sampling distribution for sample means. In this question, we're looking at, according to the Centers for Disease Control, about 36% of US adults were obese in 2013. To see if that has changed since the last study, a random sample of 250 adults will be taken. Describe the sampling distribution for the model for the sample proportion, assuming no change in obesity rates, by naming the model and telling its mean and standard deviation. Justify your answer. So P is the true proportion of US adults who are obese. We're going to take a sample of 250, and from this problem statement, I know that the true proportion of US adults who are obese is 36%. So the true proportion of US adults who are not obese is 64%. And I am told to assume that there has been no change. So this is telling me that I'm looking at proportions. The thing that leads me to proportions over means is that I am given a true proportion. They're telling me a percent, but that's going to be a proportion. There's no measured data, there's counted data. So I am going to be looking at proportions. In order to use my sampling distribution, I need to go through check-ass. I need to check my assumptions and conditions. The assumptions and conditions follow the same model for both p hat and x bar, for both proportions and means. We have to check for independence, sample size, and random. So my check-ass. Independence. I am sampling without replacement here. Because I am sampling without replacement, I am violating the independence rule. When I sample with replacement, independence is met, but when I sample without replacement, I violate independence. Fortunately, we have a rule that says if my sample is small relative to my population, I can proceed with the assumption of independence. So my population here is US adults. So 250 is less than 10% of US adults. So independence is met. So because this is very small relative to my population of US adults, I can proceed. If my population was something much smaller, like say the population of students at Cranbrook, this would not be met and I could not proceed. So the next is I'm going to check my sample size. For sampling distributions of sample proportions, in order for us to use a normal model, NP has to be greater than or equal to 10 and NQ has to be greater than or equal to 10. In this case, N is 250 and P is 0.36. N is 250 and Q is 0.64. Both of these numbers are substantially larger than 10, as we can see on my calculator, 250 times 0.36 and 250 times 0.64. These are both much larger than 10, so I am okay. College Board does require you to either write these numbers down from your calculator or to plug in N and P in your work here to show what you are checking. So we are good on sample size. And because we've met the sample size, that means that we can use the normal model. The next thing I need to check is random. When we're talking random, we either need a random sample. If we don't have a random sample, we're hoping it is representative of the population, or we need random assignment to treatment if we're dealing with an experiment. In this case, We are told we have a random sample. So I am going to say random sample stated. Because all of my assumptions have been met, I can use p hat is approximately normal. So I am done with my checking of assumptions and conditions, and I have now named my model. When we're asked to name a model, here we're asked for the mean and standard deviation, but you may be asked for the parameters of the model. When we're looking at a normal model, the parameters will be mean and standard deviation. So p hat is approximately normal. The mean of this distribution is equal to the true proportion, which we know to be 0.36. And the standard deviation of the distribution is equal to the square root of PQ over N. If I plug in these values, 0.36, 0.64, and 250, I get 0.0304. So this is my distribution for part A. In part B, I'm asked to sketch and clearly label the model. So this is the distribution of p hats. It is approximately normal with a mean of 0.36 and a standard deviation of 0.0304. I'm going to mark the mean in the middle. What is the probability that in this group, less than 25% of adults will be found to be obese? So in probability notation, this is asking what is the probability that a sample of 250 individuals will have a proportion of obese adults that is less than 25%. In my model, that looks like this area here. So the probability that a sample proportion will be less than 25%, given that this is the true distribution, we can calculate using this. So you have some options. You could turn that p hat into a z value. And to do that, I take my p hat, which is 0.25, minus the mean, which is 0.36, divided by my standard deviation, 0.0304, and I get a z-score of negative 3.62. So I could actually add another axis down here to be my z. So that's 0, and this is negative 3.62. So I'm looking for that area. So this is an older calculator. When I do my normal CDF on here, it's not going to pull up the screen, but I'm going to put my left limit, which is negative infinity. So I'm looking at the area under the curve from negative infinity up to 0.25. My mean is 0.36, and my standard deviation is 0.0304. It tells me that that area is 1.48 times 10 to the negative 4. If I go through that same process, but using my z value, so using this value, I'm going from negative infinity to negative 3.62. My mean is 0, and my standard deviation is 1, and I get basically the same thing. The only difference has to do with the fact that I rounded that 3.62 number. So if I take a sample of the population of US adults and find that if I take a sample of 250 people from the population of US adults and find that 25% or less are obese, the probability of this occurring is about 0.015%, or extremely unlikely. In the next video, I'll do an example where we look at the sampling distribution of means.